Hello, my friends and fellow electrical engineers. We meet again to learn about VFDs. VFDs are important. I'll tell you how they are simple. Okay, now why must we engineers know about VFDs in the first place? Okay, this is because the electric motor is the most important, motive power, motive power device. Anything which moves has got an electric motor inside. Okay, and out of this, more than 99% electric motors are three-phase induction motors. Got it? Why? Because these are very efficient. They are near indestructible. They can be made in flame-proof construction. Very simple. They don't have many parts. That's why they work very well. Okay. And this induction motor, while it's so good and all that, is good for running at a constant speed. That is near its, rated speed. That rated speed is a little lesser than its synchronous speed. That's about it. So you can say that more or less the induction motor will run at its synchronous speed. And till the advent of these variable frequency drives, modern VFDs, I'm not talking of old thyristor based drives and all, this speed control was very difficult. There were things like the Ward Leonard system, what do you call squirrel cage rotor current injection with a different frequency, and these are all very costly, very inefficient methods. Now, in modern microprocessor technology, they have made variable frequency drives with very good this thing, power switching devices like IGBTs and all. They have made it very useful, and magic can be done with speed control. So, if you let's say invest in VFDs for motor control, uh, they will pay for themselves back within a year or less. The energy savings are significant, but you must know how to use them correctly. Friends, let's get one thing out of the way. We'll not be covering servo drives, which are used in machine control and all that. That needs a separate body of knowledge. I don't know if I'll be able to do one in the near future, but this time we'll confine it to standard variable frequency drives that are associated with simple induction motors. Correct? Okay, you even if you heard about drives, you would have learned about some of these brands like Siemens, ABB, Yaskawa, Schneider, Danfoss, Wacom, Delta, and there are many more, including Toshiba and all. So, the important thing is, do you need to be able to use any of these drives? I mean, really meaning any of those drives. Do you need to study in great detail and find out the features of each and every drive? Let's say, if you want to know about Siemens drive, when you are now currently handling a Yaskawa or a Schneider drive. No, no, no. All you need to know is to understand the speed or characteristics of inlet. No, believe it in this. It's as simple. Okay. Okay. Now we come to understand what is this rotating magnetic field inside a induction motor that makes the rotor turn in the first place. You see, you know that there are three separate voltages. They are 120 degrees apart in phase. In the three sets of coils that are there in a three-phase induction motor. So correspondingly, there are three sets of current also separated 120 degrees in phase. Now, these currents, they set up their magnetic field. The greater the current, the stronger the magnetic field. And why the rotation of the resultant magnetic field occurs? Because there are you see the vector addition of the three the R, G, and B fields. Now, instead of showing it yellow, shown it as green, but the resultant magnetic field remains a vector sum of each individual magnetic field, and the resultant, which is the purple colored arrow, you see this rotates in space. This is how you get the resulting rotating magnetic field. Now, this beautiful animation has been prepared many years ago by Professor Mohammad Riaz, who is in the Department of Electrical Engineering at the University of Minnesota. There are many other illustrations, animated illustrations of various kinds of motors and fields, magnetic fields and all. Please visit his website. Remember, a couple of slides ago, I told you that even though you have a large number of manufacturers who make drives for induction motors and all, and their menus, their parameters all may look different. And I told you it is not necessary to study each one of them separately and all, but the better approach would be to understand the speed torque characteristic of the three-phase induction motor. Now this is very important. You know, you notice, the motor, when you start it up, it has got a starting torque of about 150%. Typically, it's 170%. Some have got even 200, 300%. It's a different thing. But it's high enough torque to overcome the starting inertia, to get things moving. And then it peaks at about the peak slip. And let's say when there is no load, it will rotate at 99.999% of its synchronous speed. Let's say 4-pole 50 hertz motor is there, which has got a synchronous speed, by the formula 120 F by P, which is 1500 RP. Which is why, the nameplate will say this motor will run giving its rated power at 1440 RPM, 1446 RPM, and things like that. What it means is when there is no load, it will operate at 1499.99 RPM. And as you go on increasing the load, the speed slightly reduces. And by the time it is about 4% less than its synchronous speed, that time it will carry enough current to carry out its full load. Now, at any lesser load, it will operate with a lower slip or at a slightly greater RPM. And let us say at around, now if we have to go on overloading it, then what happens? Suddenly at about 85-90% of its rated speed, sometimes it can be 75%, 80%, you come to what is called a breakdown torque. Now this breakdown torque is where the motor cannot move the load anymore. That is about 200 and 250%, something like that. There are motors specially made, higher NEMA classes which are there. This is NEMA B typically. That is about 220, 25% of rated speed. Any higher load, it will stall and then the motor will burn. Okay. But the important thing is to understand that the motor will carry its rated load at a small difference from the synchronous speed at about 4% less than its synchronous speed. It will bear its full load. All right. Now it is not possible to run the motor at speeds like say 70% of the speed and things like that. It's not a wise idea to run it at less than say I'd say 10% slip. That is, let us say like 1300 1400 RPM. You should not run that motor. No, it will take insane currents and then it will burn up. Don't do that. Okay, this speed torque characteristic is where it all lies. Okay, I'll explain ahead. Just remember this thing. Just remember the shape of this one, and remember these three torques. That is the starting torque, the normal torque, and the what do you call the breakdown torque. Once again, see in this particular example, the motor has got a synchronous speed or a no load speed of 1500 rpm. Okay, that time it will draw very little current. And when the speed is when you increase the loading to a point where the speed is 1440 rpm or 60 per rpm less than 1500 or 4%. Okay, 15 multiplied by 4 is 60 rpm, 4%. That time it will carry the rated current, whatever the nameplate current, it will carry the full load current. If mechanically the load is not its full load, then it will operate at a slightly higher RPM. That is between 1440 RPM and 1500 RPM. Say, let us say 1480 RPM, 1470 RPM, things like that. That time it will draw much lesser current than the uh, rated current. We'll see all these things ahead. Okay, what is the big deal with speed control? Is it not as simple as controlling the speed of the ceiling fan, which we have all seen by means of a cheap little dimmer? I mean, why do VFDs have to be this complicated? We reduce, after all, you can see the speed of the ceiling fan does reduce by when you lower its voltage. See, this is due to a different phenomenon altogether. It is not really speed control. When you lower the voltage supply to that kind of motor, which is having large blades, wind load, the magnetic field produced inside is weaker and weaker and weaker at lower and lower voltages, which are the black lines you see. These are all the speed torque characteristics of the fan motor. But only thing, when the voltage is reduced, the frequency doesn't change and the synchronous speed also doesn't change. All the same, you produce a much lower strength magnetic field. All right. So the motor wants to rotate at its full speed, but it cannot because of the lower torque, and because the torque demanded by the blades is given by the red color dotted line. So the fan will not run any higher than the speed where it intersects the load curve and the speed torque characteristics, they intersect. You follow? Now this principle cannot be applied in case of large motors. You cannot do this. So voltage control will not really result in successful control of the speed of induction motor. Just bear this in mind. Okay. Okay. In the previous slide, I told you that reducing the voltage applied to the motor as a means of reducing its speed is not a good idea, and you cannot achieve speed control. But the principle is not entirely useless. In fact, this principle is useful to reduce the starting current of the motor, which can be a very big nuisance. See, in direct online starting, the starting current can be 12, 13 times of the rated current. That is 1200%. Yes, not 120%. Okay. And you have to specially take special circuit breakers and things like that, to prevent the feeder from tripping. So in the case of larger motors, they usually use two methods. One is the star delta method of starting, which reduces the starting current kick first to about 6-7 times in a very short period. Then for a slightly longer period, that is the star phase currents, which are considerably lower. That is about 4 multiples and things like that. And then you have when the motor is in the um, final or delta phase, the starting current is much less because the motor is already moved. Okay, this is one method. Now the second method, which is of relevance to us, are soft starters. Now, unlike the two-step voltage method, in the case of star delta starters, we can vary the motor starting voltage from 0 to full voltage in a gentle gradient, slowly we increase. So there is no starting, virtually there is no starting current kick at all. So this is perhaps the best way. Now why I am saying this is these soft starters are made by the very same companies who make these VFDs, and it's important to know the application. So this soft starter is not a VFD. Very often people make the mistake of using VFDs only for reducing the starting. And no, this is a wrong misuse of the VFD. The soft starter cannot achieve speed control. The VFD, while it can reduce the starting current of the motor, should not be really used to merely control the starting current. That will be, uh, wrong use of the VFD. All right. Okay. What is lying inside of VFD? We take a look. See, this is a very simple arrangement. A three-phase full wave rectifier. There are six rectifiers which are connected, as you see in the left side of the drawing. And then the output is a DC bus. If you give 415 three-phase, this is something like 530 volts. I'm not sure. It could be 550. And then there's a large capacitor, to smoothen out the ripples. And from this DC voltage, you construct a artificial three-phase alternating current by sequentially firing those transistors. Now these are not simple transistors. These are insulated gate bipolar transistors, or IGBTs. They are very strong devices, and they are controlled by a very critical microcontroller based firing circuit, and that the logic in the microcontroller is very very sophisticated. A lot of features, all the features, the VFD and all, they contain a huge body of knowledge, and even vector calculations and many things like that are done. The entire induction motor machine model or circuit model, everything is contained in the firmware of the VFD. That is what really achieves this kind of control. And one of the features of this thing is that with modern day microcontrollers running at nearly gigahertz speed, clock speeds and other thing, these things can see short circuit happening in very slow motion. So let us say a short circuit occurs on the output terminals of a VFD. Now this is seen in very slow motion by the microprocessor inside the VFD. Okay, so that doesn't really damage. It merely goes into fault. Nothing burns up. Okay. Okay. I told you this the system of IGBT and all, they synthesize a sinusoidal wave. Not really sinusoidal. This is a equivalent of a sinusoidal waveform that is made by pulse width modulation. Okay. So these are switching devices which can switch at very high speed. Typically, these switching speeds are in few thousands of cycles per second, and each of these switching pulses, the width can be controlled, in line with the amplitude of the resultant sine wave. This is what is called pulse width modulation. Please take a look at it. But it's not a real waveform, sinusoidal waveform. This is PWM, sinusoidal waveform. Okay. Now, why this synthesized or pulse width modulated sinusoidal waveform? Because this is a synthesized waveform, alright? So you can synthesize a waveform for any frequency you want. Of course, and resultant voltage or resultant current is a sinusoidal thing. So it is possible to achieve these near sinusoidal, almost perfect sine waves at any frequencies. So just like you can vary the frequency, and by merely controlling the firing sequences, the firing frequency, the and you can fine tune many of the parameters of this pulse width modulation to get really sophisticated control. So as an overview, what happens really is when you reduce the frequency, let us say a motor is ordinarily supposed to run at 50 hertz. You want to run the motor at half the speed, so you reduce the frequency to 25 hertz. Now it will have a corresponding, almost similarly shaped, speed torque characteristic, which will behave identically. It will interact identically with the load at half the speed. Okay, not only at half the speed, at any speed, even beyond the rated frequency. What happens at higher frequencies, I'll explain in the next slide. But this is the important thing. It is by maintaining the same kind of speed torque characteristics at any speed, higher or lower. Okay, that we have perfect speed control, torque control, and other things. When you use a VFD, it has to be seen in terms of this diagram. That is the general shape of the speed torque characteristic, that is its starting torque, its breakdown torque, its load torque with respect to its rated slip at any frequency will be similar to what it was at its rated frequency, which is why with a VFD you can have very good speed control at any speed. Now this is the thing which needs to be remembered. Now the animation is shown on this slide, they are also taken from that Mohammad Riaz's work, as I have referred to earlier. It very beautifully shows the speed torque characteristic at varying frequencies, right? And it also shows how the current, also increases with speed. The current doesn't increase in such a broad range. For all practical purposes, the speed torque characteristics is just the same as it was at full load. In the diagram at the top right shows what happens suppose you were to go at frequencies higher than the rated frequency. A very interesting thing happens, that is called field weakening, and this is an important principle in certain applications. See, you have to bear in mind, when you increase the frequency, the because of its inductance, the motor coils are almost pure inductances. All right. So when you increase the frequency, so also linearly its impedance will go. Now you can't run the motor at 100 RPM and hope that it will draw the same current. Why? Because 2 pi FL, or the impedance is twice at 100 hertz as it would be at 50 hertz. So then when you draw a lower current, you get a lower magnetic field, which has to in turn interact with the correspondingly lower, stator current to produce the torque. So what happens is that the torque of the motor falls inversely in proportional to the square of frequency beyond its base frequency. Uh, Up to that, from 0 to its rated frequency or 50 hertz, which is the base frequency, from minimum to base frequency, the diagram shows that the maximum torque and the rated torque and all these things are relatively the same. But when you cross the rated frequency, base frequency, then while you can still safely run it, The motor will not burn or anything, but it will not be able to deliver the same torque. So you can use it at higher frequencies right up to 400 hertz. The average VFD can go up to 400 hertz, which is 8 times its this. But for this, the other parts which are like a motor and belt and pulley and gearboxes and whatnot, other parts of the machinery should be able to run at higher speed without getting damaged. And then there are inertial considerations also, like when you want to rotate at very high speeds and things are running at 8,000 rpm and not a simple thing. Mechanical considerations, safety considerations, you know you have to have a clear idea about the dynamics, about inertia, the braking time, and so many other things. Yeah, that's it has to be seen on a case by case basis. But yes, you can run it, but then bear in mind the torque will reduce, and you have to also keep in mind that you're likely to have higher wear and tear at higher frequencies. And first of all, the motor should be in fact capable of running at uh, you know 8 times its rated speed. So let's say instead of uh, 1500 um, RPM, can the thing really run at 12,000 RPM? Now, when you look at the things this way, you'll find that smaller motors with low inertia, they can run at much higher speeds. But you cannot run a average sizable motor, in the horsepower in kilowatt range, 2 kilowatt, 3 kilowatt at tens of thousands of RPM without the motor actually being designed for that kind of application. All right, just bear that in mind. Now, as I told you, varying the frequency will achieve almost linear speed control. Means if you take a 50 hertz motor which is supposed to run at near 1500 RPM at 50 hertz, all right, you reduce the speed to 5 hertz, all right, or 10% of its rated frequency. Obviously, the motor will run at about 10% of its speed. It will run at 150 RPM instead of 1500 at 5 hertz. Yes, that's the way to see it. But one important thing is what happens to the voltage? Again, see, as I told you, the torque is proportional to the current run by the motor. Or more exactly, it is the current in the rotor of the motor. Now, this is usually a squirrel cage. And the squirrel cage currents have to be seen as the secondary currents of a transformer, because a magnetic coupling that is similar to what exists between the primary and a secondary windings of the transformer, you know, a similar phenomenon takes place. Whatever is the current in the stator of the motor and the rotating magnetic field, and also along with the slip, the degree of slip will induce secondary currents in the stator. It is these currents that interact with the rotating magnetic field and produce torque. All right. So if at 5 volts, if at 5 hertz, you want the same torque as you are getting at 50 hertz, that means the current taken by the motor at 50 hertz should be the same as it is taking at 5 hertz. So this is possible by linearly reducing the voltage along with the frequency. Why this is so? Because just like any other inductance, the impedance, that which for which limits the current, this is linearly proportional to frequency. All right. So half the frequency, you have to apply half the voltage. 1/10 of the frequency, the motor will give you the same current when you apply 1/10 of the voltage. Yes, this is how it works. So reducing frequency or changing frequency to achieve speed control is one part of the thing. Simultaneously, you also to control the voltage in a near linear manner. See, for special applications, when you want a torque boost and things like that, or to handle some peculiar load characteristic, there may be minor deviations. As you can see on the diagram on the right, there is uh, a little lower voltage than the linear at 30 hertz. Somehow 40 volts is given. But these are generally along the same principle. That is, the lower the frequency, you can you must lower the voltage. Though it may not be necessarily linear, it has to be sufficiently in line. Alright? It may be little lower, it may be little higher by a small amount. Okay. Now, how this voltage varies with the frequency is the basic idea behind configuring a drive. This aspect of configuring the voltage with respect to the frequency, or what is called a VF pattern of the drive, is the essentials of configuring a drive. Now, for most mechanical loads that needs constant torque, that is, the torque doesn't have to vary with speed, then you configure a linear VF pattern, that is, voltage and frequency are varied in a linear manner, as you see on the diagram on the left. When it is not linear, you can have a much lower voltage at lower frequencies, finally leading to full voltage at full frequency. We'll see in the next instance of this series about VFDs how that is done. And that principle is what leads to energy savings and all that. But in any case, this VF pattern has to be configured so as to match the corresponding speed torque characteristic of the load. Okay, we should not have more current than that is needed. We should also boost the current if the load so happens to demand. That is the essentials of configuring the VF pattern. Okay. Okay. Now, to those who are absolutely new to VFDs, I think this is enough for a single session. It is better to wait a bit before going on to the next stage. It can be a little more confusing. Correct. There, you to understand loads, and that I will cover in the next one. And there's one more third session in this series where I'll be helping you understand what is harmonics and other problems associated with VFDs and how to control them. Okay. I hope your time was well spent. Thank you for listening to me. Hope that this material is useful. Please feel free to voice your opinion in the comment section, and your feedback is very important to me. Thank you.